7. Okay, so it looks like someone wants to do 7. 7 is a 3-meter long rod initially at rest. It's subject to 3 forces shown on the diagram and no other forces which produce any torque. Will these forces cause the rod to rotate about the pivot shown, and if so, in what direction? Okay, so with this one, right, we are looking at whether it's going to rotate clockwise, counterclockwise, or if it will rotate at all, right? And so that's kind of dependent on each force and how much torque it's going to exert, if any torque at all, right? So one of the most important principles is obviously to understand what the torque equation consists of, right? So for the torque, we have F, our force, right, times our radial line, so the distance along the radial line, the force is from the pivot, and then times sine of the angle that's sandwiched in between the force and the radial line. So in this case, they have the problem set up like this, where we have this rod, we have a pivot right here around this location, we have a force acting at the pivot at 50 newtons here, and then another force of 60 newtons pushing upwards like this. That's 1 meter to the right here. And then another force at the very end here, that's 30 newtons, and that is 2 meters to the left, right? So each one of these forces is going to be exerting some kind of torque, or at least we can consider them, right? Or consider looking at like what torque it generates, or if at all, right? So first off here, what do you recognize about one of these forces? What is immediately noticeable here? So yes, there is going to be one force that's going to be exerting absolutely zero torque, right? Now, which force is that? At 50 newtons, right? Excellent. So that's because if you're at the pivot right here, right, everything is measured relative to the pivot. So the pivot, right, is our central point here, and we're measuring from it. So this R is going to be that distance away from the pivot, basically. That's the distance away from the pivot along the radial line. So if we're exerting a force at the pivot, we should expect zero torque. We shouldn't expect the object to rotate at all. So this R would essentially be 0 for that force right here. Right, so if we label 50 Newton force, you can say that has 0 torque. Right? Once again, that's because the radial line, or the distance away from the radial line, is going to be 0. And a nice way you can kind of think about that and relate it to real life is like if you're trying to open a door and trying to like push it open at the hinge, it's not going to rotate, it's not going to open because you're pushing at the hinge. You're not pushing away from the hinge because the hinge is the pivot, right? So at that point you have 0 torque, right? So now it's kind of down to the other two forces and determining now, well, do these forces, for example, like do they cancel out, right? If they would cancel out where you have 0 torque, then it would be no rotation. Or does one force kind of overwhelm the other and offer some kind of torque, right? So what we can do here is kind of write a net torque equation, right, to figure out exactly how these forces are going to interact with each other, what kind of torque they're going to, exert on the rod, and then from that figure out whether it's going to rotate or, right, if it's, like what direction is going to rotate, or if it rotates at all, right? So if we have this 60 Newton force, let's start off with that on the right here. So this 60 Newton force, 60 newtons is a force. Obviously, it's located at a distance of 1 meter, right, from the pivot. Now, keep in mind, like, when you're doing torque problems, you do not have to consider, like, oh, if this is 0, then this is, like, +1 and this is -2, like, because it's not, we don't have, like, a specific axis or anything like that. It's just simply the absolute value of, the distance from the radial line. The center of mass equation is when you would actually want to include like positive and negative numbers relative to your origin point or your pivot. Otherwise, for your torque problems, going to the left or going to the right, doesn't matter. What does indicate any sense of direction, right, or any sense of sign, right, being negative or positive torque, is what direction the rod essentially where it's going to rotate in. So if it's clockwise, it's negative. If it's counterclockwise, it's positive, right? So since we have this force at 60 newtons, and it's at a distance of 1 meter, and then our sine of the angle here, right? So this is directed at what angle? 60 newtons is directed at what angle here? (90°), excellent, right? Because you have the force, right? You have this force here. Let me do another color real quick. You have this force, and you have the radial line, and then you have the angle that's sandwiched in between, right? So it's a 90-degree angle right there. And sine of 90, right? Sine of 90, if you calculate that out and make sure you're not in degrees, make sure that that you are in degrees, that you're not in radians. In sine of 90, you should be able to get 1 for that, right? And that's something you should just obviously memorize for this, right? Sine of 90 for these torque equations, especially when you have something that's directed at right angle like this, is going to be 1. So this essentially ends up being 60 Newton meters, right, for our torque. Now, here's how you can figure out whether this is going to be positive or negative, right? Whether it's going to be clockwise or counterclockwise. So the trick that I have, because I know some students will have trouble with visualizing what direction it kind of goes, is if you make whatever rod you're looking at, make it a pencil, basically, right? So you can hold up your pencil like midway during the exam. This is literally what I would do. I would hold the pencil at whatever the pivot point it was, right? So sometimes the pivot point is, normally like just at one end, right? Either on the left end or on the right end. But other times it's going to be somewhere like in the middle, like with this problem, right? So you can hold the pencil, and I'm doing this like as we're speaking, like I'm holding my pencil right now. So you can hold the pencil, right, at that pivot point, and then with 2 fingers for let's say your left hand, right? And then with your right hand, push in the direction of that force that you're looking at. So if I hold the pencil with my left hand with 2 fingers, pinch it with my thumb and my index finger at that pivot point, right? And then push up with that 60 Newton force in that direction upwards like that, what you notice is that you can think about your pencil as being like an arm on a clock, right? And so if you push upwards in that direction, right, that's going in the counterclockwise direction, right? It's going in the counterclockwise direction. So let me kind of draw that out here real quick. So you have, here's your pencil, right? Here's a little eraser. If this is my pivot point right here and I push upwards like this, I notice that the pencil kind of gets pushed up and to the left, right? And that's kind of going back in time, right? That's counterclockwise. So we would label this as a positive torque, right? So positive 60. With the 30 Newton force now, we have 30 newtons as our force, 2 meters as our distance from the radial line from the pivot, or distance along the radial line from the pivot, right? And then it's also directed at an angle of 90 degrees, right? What you notice is that it's also 60, but is it positive or negative? Well, if we do the same trick, right? If we do the same trick, then, let me erase this here real quick. If we do the exact same trick here, maybe now hold your pencil with your right hand, for example, with your right index finger and right thumb, right? Here's your pivot, right? I'm doing this as we speak. If I hold it at the pivot with my right index finger and my thumb, and I push upward with that 30 Newton force in that same direction, what I notice is that the pencil kind of goes upwards like this. So here it is, the eraser, right? What you notice is that's going kind of like forward in time, right? That's clockwise. So if it's clockwise, it ends up being negative, right? Clockwise is negative direction for torque. Counterclockwise is positive, right? And so this ends up being negative. And what you notice here is that if you end up writing a net torque equation, right, where you say like, okay, now I want to look at the different torques here. So we have torque due to the 60 Newton force. We can say that's positive, right? So T60, and then minus T30, right? And I'm integrating the negative sign here, so I can just plug in the magnitudes for my values. So I know 60 minus 60, that's just going to be 0, right? So I should see no net torque. This system would essentially be in static equilibrium, right? There would be no motion. And at this point, we would see that it would not rotate. So C would be the answer for that. Oh, yep, thank you for letting me know, Daisy. I kind of missed that. Problem 5 in exam B. Daniela, did you have a question? Okay, no worries. All right, so let me hop to 5 on exam B here. So 5 on exam B is a very unique type of problem that I don't remember if they really kind of went over it um, like in your lecture slides. I do remember it was in my lecture slides that Dr. DeJong had mentioned like very briefly a problem like this was going to be on the exam. Um, and it's all having to do with um, like how you can generate like artificial like force of gravity in space. So we kind of like mentioned it very briefly. So let me kind of go back and pull that problem up here real quick and take a look at it. So this is 5 exam B. All right, give me 1 second here. Yeah, there's audio. I'm speaking. Like I'm just like taking a minute to pull up the problem here. My bad. All right, got it. So in outer space, where the force of gravity can be neglected, an astronaut in a rotating space station will still have apparent weight. Okay. Consider an astronaut in a cylindrical space station with a diameter of 0.2 kilometers rotating about its axis. As shown, what is the period of the rotation if the astronaut's apparent weight in the space station is the same as the actual weight on Earth, right? So here, let me draw this out here. So the person is kind of standing in this, what do they call this? Is rotating space station, okay. And really when we think about apparent weight, we're referencing the sum of all contact forces in the system, right? So the contact forces in the system here would be your normal force, I believe, right? Because really the only surface of contact that the astronaut is experiencing is the actual space station itself, right? Whatever they're standing on. You can kind of see that in the image, right? So if this is our surface of contact, then normal force is pointing this way, right? And so what do you notice here? Like this is a big circle, essentially, right? And we have this normal force pointing towards the center of this huge circular space station, right? What kind of, idea do you think would come to mind about how we might go about considering relating this force to something else? I guess it's kind of a weird question, but like whenever you see a force pointing towards the center, what should you kind of think about immediately? Since his apparent weight is the same as on Earth. Yeah, essentially, we're in space, so I guess we wouldn't technically have gravity, but um, since his apparent weight is the same on Earth, then basically his normal force, right, would be equal to the force of gravity or his actual weight on Earth. So that, excellent, right, is what we're looking for to figure out specifically this value of normal force. But even better, right, also excellent, we would think of centripetal acceleration, right? So whenever you see a force kind of pointing towards the center like this, like it's always kind of a trigger like feeling that you're like, okay, well if I see a force pointing towards the center, like it probably has something to do with like some kind of centripetal force, centripetal acceleration, or something like that, right? And the reason why you want to think about that is like, okay, if I have this force, right? If I have this force and they're asking me to figure out period, well, how, like, what does that have anything to do with force, right? Well, if a force is pointing towards the center, right? Here's like the method of thinking that you can kind of go through, right? So I think about force to center, right? If a force is pointing to the center, I think about, okay, that's a centripetal force. I think about centripetal force and I'm like, okay, centripetal force, cool. Well, centripetal acceleration then, right? Let's think about centripetal acceleration. Well, what about centripetal acceleration? Well, what's the equation for centripetal acceleration, right? V squared over r. Well, now we're getting somewhere, right? Now we're getting somewhere where you have your radius, right? We can figure that out. We have a diameter. We can figure out the radius pretty easily. We have this V. Not quite sure how to like take care of this V here. But what do we also know about our velocity? What do we know about our V, our speed? There's also a way you can kind of rearrange that equation, right? There's, or at least there's an equation for speed, right? Anyone remember what the equation is for your speed, or like your linear speed or your linear velocity? Anyone remember that equation? Excellent. So r times your angular speed, right? And if we expand that, right, so we have v is equal to r times your angular speed. And if you keep up with my videos on YouTube, you probably have heard me refer to this omega Greek letter here as the fancy W. I don't know why. I did that my first semester of peer leading for physics, and it just kind of stuck. But this fancy W here, right, is our angular speed. And we can expand this equation further, right, and think about, okay, well, now it's 2 pi r over t, right? And that's an equation that you can find on your equation sheet pretty easily as well, right? 2 pi r over t. Well, now we're, hitting the jackpot, right? Because we have a radius, we have this period, this t, right? And now we also are able to figure out the normal force, right? Because they said the apparent weight, which would be your normal force because it's the contact, some of the contact forces, you're able to figure out the value for period pretty easily here. So if we have normal force, right? If you have normal force, then once again, we think about this as being the only force that's going to contribute to the centripetal force right here, right? Because it's pointing towards the center of the circle, right? And normal force is referring to the apparent weight in this case because the apparent weight is the sum of all of the contact forces. Are you guys experiencing delays between what I write and what I say? Oh, shoot. Oh, man. Really? That's phenomenal. Well, I'm not quite sure what to do, to be honest. Like, okay, let me see here. I want to see if I can do something about it, like lower the resolution of the screen sharing or something. This is why I hate like using Zoom and Blackboard Collaborate. For some reason, they have an issue with my internet. Let's see here. Yeah, it doesn't look like there's a way that I can lower the resolution of the streaming, but like you guys can still hear me, right? Like my voice isn't cutting out or anything like that. It's just a delay of what I'm writing. Okay, phenomenal. All right. So hopefully, like, yeah, I don't know what to do about the drawing, to be honest. I can try and like slow down what I'm saying to like give you guys a chance to like, I guess, interpret and catch up. The symbol for period is that little, or the capital T, right? If you have that equation, linear speed is equal to your radius times your angular velocity, that's equal to 2 pi times your radius divided by your period t, capital T. Uppercase T is the period. And so, like we said before, right, the apparent weight is the sum of all contact forces, and the only force that's really acting as a contact force in this case is the normal force, right? Because the only surface of contact that we have is the actual space station itself, right? And then the astronaut standing inside that space station, right, will feel the normal force kind of the space station pushing up against the astronaut himself or herself, right? Because basically the normal force would essentially kind of keep the astronaut from like sinking through the space station and dying, basically, right? So really the only contact force here that we have, right, that's based on the surface of contact is going to be the normal force. And since the normal force is pointing towards the center, like we said, we're going to want to think about the normal force as contributing to the centripetal force. Then, from looking at normal force is equal to centripetal force, right? Normal force is equal to centripetal force. Well, centripetal force is equal to mv squared over r, right? mv squared over r. Your mass times your velocity squared divided by your radius, right? Well, the problem also stated that the apparent weight, which like we said is going to be the normal force, is actually equal to the real weight of the person or the actual weight of the astronaut on Earth, right? So that means that the normal force is simply just also going to be equal to the force of gravity, right, on Earth. So that will just be equal to the mass times gravity, mg, of the person, right? So Fn would just be equal to mg. So you have mg is now equal to mv squared over r. So all we did was substitute mg, the force of gravity, instead of the normal force, because the last sentence of the problem said they're equal to each other anyway. That helps figure things out because mass will cancel out on both sides, right? You have mass on both sides, so you don't have to consider the mass, right? Which is excellent because we're not really given the mass anyway. And then you have g, your gravity. You can multiply over your radius, right? So g times r is equal to v squared, right? And then we said that your v is equal to your radius times your angular velocity, and that's equal to 2 pi r over t. So that's like saying 2 pi r over t is equal to your velocity there, and then squaring that whole term, right? And that's equal to gr right here. Now, this is really just a matter of plugging in values after this, right? We have g is equal to 10, because that's 10 meters per second squared. So 10 times our radius, right? So the diameter is 0.2 kilometers. So the radius would be half of that, which is 0.10. But it's in kilometers, right? We want things to be in meters. So if the radius is 0.10 kilometers, right? So we can multiply by 1,000 to figure out the value in meters, right? So 1, 2, 3. 100 meters there, right? That's our radius. And then we can plug that into the equation here. 10 times 100, g times r is equal to 2 pi r over t, and then that whole thing squared. So 2 pi r, where r is going to be that 10, or that 100 meters, my bad. And then t is your unknown, and then this whole thing squared, right? Let's see here. I want to calculate this out real quick. I'm going to grab a calculator so I can make sure that this is done correctly. So we have 1,000 here on the left. And then 4, basically pi squared, essentially. And then times that, okay, times 10,000. And then divided by t squared, all right. And if we multiply over t squared, divide the 1,000 over, let's see here, I think that should That should check out, I think. Let me double check real quick. Yeah, you get roughly like somewhere around 400 for that part on the right here. So t squared is equal to 400 roughly. And then if you take the square root of that, your period should be 20 seconds. Yep, exactly. I can't remember who had asked that question, but does that kind of make sense how to like break it down, move from the normal force to the centripetal force to centripetal acceleration, and then figuring out the period like that? Awesome. Okay. Any questions at all? I'd be happy to explain it again, or yeah, let me scroll up here. Is that good, Daisy? Okay, awesome. But yeah. I see someone said they wanted to go over 15 and 16 on exam A. And yeah, this was pretty much just like substituting values in. But it's also like a little heavy on the interpretation end of things because you have to understand what apparent weight is. You have to recognize that the apparent weight is the sum of all contact forces. The only contact force that we have here is normal force. Normal force is pointing towards the center, right? Because it's perpendicular to the surface of contact. And if your surface of contact is simply the space station, then here's the surface, right? If we were if the astronaut was literally just like standing here, right? Then there's your surface of contact. There's your normal force pointing perpendicular to that surface of contact, right? So we obviously have to understand normal force as well. And then you can see that the normal force is pointing towards the center. A force pointing towards the center is going to be a centripetal force, right? It's going to be contributing to the centripetal force. And then from that, you can substitute things in exactly your centripetal acceleration and then your period stuff, right? To be able to figure that out. But it's a very daunting problem like at the beginning because you're like, okay, well, I don't really have much other than like the radius, right? And I have a diameter and I have this random information about like apparent weight and actual weight. And it's like a little bit confusing to figure out where to start exactly. But the idea is that you want to first like write down the information that you've collected, that you've interpreted, and that's how I go about like solving physics problems, is that you list out all the information that you have, right? So for that last sentence, for example, we recognize that apparent weight is equal to actual weight. So, okay, apparent weight is going to be equal to mg. What is the apparent weight? Okay, well, then I go back and interpret some of those things and figure things out that way. So just kind of like step by step, writing the values that you have, and then writing the values down that you don't have that you want to figure out, and then kind of trying to connect them together, like via an equation or some concept or something like that. But yeah. Sound good for this problem 5? Any other questions about this one? All right, I will take that as a no probably. Someone had asked to go over 15 and 16 from exam A. All right, so 15 and 16 from exam A. Let me move over here. Oops. 15 exam A. Yep. Okay, so 15 says, consider a horizontal spring that is attached to a block at one end and tethered to a wall at the other end. Okay. A pulling force, F pull, is exerted on the block, and the spring gets stretched. A force of 15 newtons is required to keep the string stretched by 0.05 meters. Okay. How much work is done by the pulling force to stretch the block from its equilibrium length to an extension of 0.05 meters? So we have this force. Okay. So this force, this pulling force, right, is equal to 15 newtons, right? And that keeps the spring stretched by 0.05 meters, right? So, all right, cool. And the distance that it's stretched by is 0.05 meters, and they want us to figure out work. Well, that's some interesting information there, right? So that's a great question. What does that mean, keeping it stretched by 0.05 meters? My initial thought to approach this problem is exactly interpreting that statement, right? What does it mean to keep it stretched by 0.05 meters? So if you're keeping something from, like, the word keep is like a key word here. Like, it's very weird to think of it as a key word, but very, like, I'm pretty sure that, yeah, this is essentially how to approach it. And the key word here is keep. And so with a spring, right, whenever you have a spring that you stretch, what does the spring tend to want to do if you stretch it or you compress it? What is it going to want to do? Revert back, right? Go back to equilibrium, right? And that's the idea of the spring force. The spring force is strictly referred to or defined as a restoring force. It helps restore the spring to its original position. So if we're keeping the spring stretched by 0.05, right? We're keeping it stretched. Well, then wouldn't you be directly opposing the spring force? Because the spring force wants to bring it back to an unstretched version of itself, back to equilibrium, but you're keeping it stretched, right? So if I pull on a spring and I don't let go, I keep or I maintain that 15 Newton force, right? Then is the block spring system really in motion? Is it moving at all at that point? No, right? And so what that means is our F pull to the right. So if we pull this, if we have this spring, we pull the block right here to the right, F pull X to the right. That's a positive 15 Newton force in the positive X direction. In order for there to be absolutely no motion for the spring whatsoever, then there has to be a negative 15 Newton force to the left that would cancel everything out, right? And it just so happens that this negative 15 Newton force is exactly what the spring force would have done anyway, right? Because if you stretch it to the right, the spring force is going to want to restore it, revert it back to the left, right? So our spring force would be equal to a negative 15 newtons in the opposite direction, right? So awesome. Now we're kind of getting a little bit closer to what we want to do. So FSP, right, our spring force, the equation for that is going to be negative kx. Negative times the spring constant times your distance compressed or stretched, right? Or delta x usually, or delta L is what they define it as, right? And the reason why there's a negative here is because if you think about it, if I stretch something to the right, I'm going to have a positive x, right? I'm going to have a positive x if I stretch something to the right. The spring force, considering the fact that it's a restoring force, it's supposed to restore things to its original position. If I stretch something to the right, what direction is it going to go back to? If I pull it to the right and I let go, exactly, it's going to want to go back to the left. So that's why we have this extra negative sign thrown in to basically oppose or restore whatever like change you made to the spring. So if I stretch it to the right, I have a positive x, my force would be negative, the spring force would be negative in order to restore it to the left. If I compress it to the left, if I push inwards, right, to the left, then I have a delta x that's going to be negative. So negative times a negative would be a positive. That makes sense because then the spring force would want to restore the spring to an uncompressed state back to the right. So we have this FSP is equal to negative k delta x. Well, we know that now the negative 15 newtons is our spring force, and we have this negative k delta x. Well, why are we even interested in looking at the spring force at all? Well, it kind of goes back to really what we're trying to figure out in the end, which is how much work is done by pulling by the pulling force to stretch the block from its equilibrium length to an extension of 0.05 meters, right? So work in this case is going to be defined in either one of two ways, right? So normally you might see work defined as force times distance times cosine of the angle between the force and the distance, right? But it's better here to consider the work, what was I going to say? Shoot. Yeah, so we want to look at work, right, with the, specifically the spring force in mind here. And so if we have this spring force, right, and it's supposed to be, you know, doing work over a specific distance, well, the spring force is not a constant force, right? And if you look at the graph actually as well, for your F pull, your force is not constant. It increases over time, right? Or as you increase your distance, the F pull increases. So either for the F pull or for the spring force, what you notice is that you don't have a constant force. And for you to be able to use this work equals force times distance equation, you have to have a constant force. That force must be constant to be able to use this equation. So what a lot of people might do is simply just plug in like, okay, 15 newtons, right? And then multiply by the distance, which is 0.05, and then you get, okay, 0.75. I plug that as my answer, cool. But what you don't notice here is that the F pull, right, the F pull X, or even the spring force for that matter, they're both forces that are not constant, right? As you stretch the spring more, or as you compress it more, the magnitude of the pull or the spring force will increase, right? The fact that this isn't a constant force that we're dealing with invalidates the use of this equation. This equation must use constant force, right? So instead, what we're going to have to look at is consider work in another term, right? Which is looking at the work energy theorem, right? Work is equal to the change in energy that we observe in the system. And we know that the change in energy observed here, right, is going to simply just be as a result of the spring potential energy, right? So you don't have, I mean, obviously you have kinetic, right? You do have kinetic, like energy here that's at play, but the only thing here is that there's no way for us to really like precisely kind of consider that at the moment. So we're just interested in the spring potential energy for this part, right? So what we do is connect these two and think about, okay, well, the work is just going to be simply equal to the spring potential energy here, right? And spring potential energy is going to be equal to half kx squared, right? Half times your spring constant times the distance that you compressed or stretched squared, right? Well, we have our x, but we need to figure out our k, and that's where this part comes into play here, right? We have this negative 15 newtons, that was our spring force, is equal to negative k, and that was multiplied by the stretch distance, which was 0.05 meters, right? So if we figure out the K, we're going to be able to figure out the spring potential energy, and therefore the what was I going to say? The work. Yeah. So K, I believe, is 300 for here. And then if you plug in 1/2 times this 300, and then times your distance compressed, you should get 0.375, which is the correct answer here, right? So we're considering the work as being, done, or referring to the spring potential energy, as opposed to work is equal to some constant force times the distance, because in this case, either the spring force or the F pull force, and that's really good that they gave you the diagram there to be able to understand that, is that you see here that the the F pull force from that little diagram that they showed you, it's not a constant force as you increase the distance that you compress or stretch it by. And so because it's not a constant force, we're not able to use the work is equal to force times distance equation. So we instead have to refer to the work energy theorem, right, to relate work as being, due to, or work is equal to some kind of change in energy, and that change in energy is equal to a change in the spring potential energy. And so here it wouldn't be negative, it would be positive. The K that we figured out ended up being positive because we had a negative 15 on one end and a negative K on the other. So the negatives canceled out and we were left with a positive 300, and then K is positive 300, and our distance that we stretched it by, that was a positive 0.05 meters. So we should end up with a positive 0.375 joules for this. But yeah, I mean, really the key is understanding that keyword keep, right? Keeping the spring stretched means that you're preventing it, or you're directly opposing the spring force. So the spring force would simply just be equal to your pull force that you were holding it with, right? From your spring force, you're able to figure out then your spring constant. Well, why do we need our spring constant? Because they're asking us for work. Well, how can we figure out work? Immediately we think about force times distance. Is this a constant force that we can use? No, it is not. Based on the diagram, the force changes as you increase your compression or stretching distance. So we can't use the work equals force times distance equation. How can we figure out work otherwise? Use the work energy theorem, right? So we notice here that really the only change that we would observe here in the energy would be the spring potential energy. Because if you think about it, right, if we have this spring stretched initially, so you might ask okay, well, where does kinetic energy play into this? Because if we release the spring, isn't the block going to move and then have kinetic energy afterwards? Well, if we start off with an initial kinetic energy of 0 because the object isn't moving, and then we let it go back to its equilibrium position, well, at its equilibrium position, it's not moving either. So its final velocity is also 0 once it's at rest at equilibrium. So we don't want to factor in kinetic energy, and there's no way for us to do that even if we wanted to, because we don't have any values or way of figuring out the velocity here. So really the only thing that we'd be interested in here is the change in the spring potential energy. Something like gravitational potential energy also doesn't factor in here because you're not changing the height of the system at all, right? Because gravitational potential energy is mgh, so no change in height means no change in gravitational potential energy. So really the only thing at play here is the change in the spring block system here, the spring potential energy. And that's how we can figure out the force, or the work. How I could tell the force wasn't constant on the graph? So if you look at the graph there, at 0.05 meters, it's 15 newtons. If you pick a point, 0.025 meters, that might have been 7.5 newtons. So you can see that as you increase your stretching distance, or as you compress it more, which would be to the left, right? As you move along the graph, you're increasing the magnitude of your force. So that's why it's not constant. If it was constant, then for whatever distance, it would just be a horizontal line. It would be a constant 15 newtons for every single distance that you pull, right? So if I pulled at to a distance of 0.01, that's 15 newtons. If I pull it to 0.02, that's 15 newtons. If I pull it to 0.06, that's 15 newtons. But what you can see here from the graph is that that force continuously increases as you compress more or as you stretch more. You started off at 0 newtons with nothing, right? Then you might have had like 2 or 3 newtons, then 5, then 10, then 15 right there at the 0.05 meter mark, right? Same thing if you compress. And that's why that's not constant there by the graph. Does that make sense? Awesome. And does the like general like idea of the problem also make sense as well? Like how we went from this idea of a pulling force to the spring force to, you know, figuring out the spring constant and then work, and why we can't use the work equals force times distance equation. Does everything kind of gel together in that sense? Okay, awesome. Any other questions for anybody else as well about this problem? Yep. Okay. Sweet. So with that, I can move on to number 16. Number 16 is going to be a lot quicker. It says during the construction of a high-rise building, a 40-kilogram block is lifted vertically upwards 20 meters from the surface of the earth at a constant speed. What is the work done by the lifting force? So work, right? You go to some kind of change in energy. We can use the change, like the work energy theorem, right? And so really, there are some keywords here that we have. So we have constant speed. If something is moving at constant speed, right? If we were to analyze its kinetic energy, initial and final speeds or initial and final velocities would be the same because you're moving at the same speed every single point. So there would be no change in kinetic energy, right? So if we had kinetic energy here, that would be 0. There's no spring potential, right? Because there's no spring, but there is some kind of change in the height. So we should experience some kind of gravitational potential energy, right? And so that work is equal to the change in gravitational potential energy, right? Delta UG, and that's equal to UGF minus UGI. Well, if you're at the bottom, right, then UGI would simply just be 0, right? Because this would be MGHI. If you're at the surface, right, of the Earth, where you're just at the bottom there of this building, then we're assuming that's our initial height, and that would be 0 at the bottom. And then you move 20 meters upwards, right? That would be your final height. So MGHF, HF being your 20 meters there at the top, right? Now it's just a matter of looking at work is equal to MGHF, right? So we have mass is 40, our gravity is 10, and our height at the top there is 20. And if you do that, you should be able to get 8,000 joules. And, you know, we can confirm this idea of the fact that work equals force times distance. It's only applicable for constant forces. Well, if we wanted to solve this by work equals force times distance, what is the force in question here? It would be a lifting force, right? They define it as a lifting force. Now, this lifting force, right, we're assuming that it's like, now that I'm thinking about it, well, might be a little bit, yeah, I don't think maybe you'll be able to do that, because then you could figure out the work done by gravity, and then that would give you the exact same answer, because the force of gravity, that would be mg, and then your distance that you acted, that force acted on was 20 meters, so you'd have the exact same value there. But they're specifically asking about the so lifting force. Yeah, I mean, I guess if you lifted that weight, right? Yeah. So since it's at a constant speed, we're not experiencing any acceleration. So really the lifting force and the force of gravity would kind of cancel out on a free body diagram. So if you were to have, here's this block right here, force of gravity, and here's your lifting force, we don't want there to be any like sort of acceleration. That's why we have a constant speed. So your lifting force would be equal to your force of gravity. So you could simply just kind of like substitute things in, where you could say, okay, here's my lifting force. I want to figure out the work done by it. It's applied over a certain distance. The lifting force just so happens to be equal to the force of gravity because everything's at constant speed. There's no net acceleration. So F lift is equal to Fg, and then that's equal to mg, and then times the distance at which that force is applied, and that's 20 meters, and that also can help you figure things out. And that matches up with our like reasoning for number 15, that the work equation force times distance is only applicable for constant forces, because if you think about gravity, gravity is a constant force, right? Or at least it has a constant like acceleration due to gravity, right? And assuming obviously like the block doesn't have a changing mass, then every single point it would have a constant force of gravity, right? Assuming that the mass doesn't change or anything like that. Now, because of that, right, we're able to use this work equals force times distance equation because you have this constant force of gravity, and that's equal to the lift force. And that checks out, right? As opposed to number 15, where the spring force or the pulling force kind of changed over time, or as we, increased compression or increased stretching. So, yeah, I mean, either equation would work. I tend to like to do a little bit more stuff with the work energy theorem. I like to relate things back using this equation here. It's preferable, I think, because usually, especially once you get to like the written problems, the most common like way that you're going to be solving problems with like work and energy and everything like that is that you're going to be using that work energy theorem to internalize like forces and internalize energies, as opposed to externalizing them using the work equals force times distance equation. But it's important to understand the difference between them and when to use them at. But yeah, so hopefully that kind of makes sense, that distinction of when to use either equation. Someone like, you want to go over the written problem for exam A, the first one. First written problem. Okay. Yeah, we can do that. Is everyone okay as well with number 16 for exam A? Any other questions? Okay. Yeah, so I'll do written problem 1 on exam A, and then we can go to written problem 3 on exam A, absolutely. Written problem 3 on exam A is fun. I like these center of math problems. So let me see here. Problem 1. Hopefully this one shouldn't take too much time. It's like centripetal force and acceleration. That's pretty nice. So let me make some room here. So problem 1 for the written on exam A. So we have a car goes around a circular track that has a radius of 310 meters at a constant speed. It takes the driver 4 minutes to circle the track 3 times. The car experiences a centripetal force of 4,600 newtons. Part A wants us to draw the free body diagram as viewed from behind the car. Label all forces using only subscripts. Okay, so if we're, standing behind this car as it, makes a turn, let's say it's making a right-hand turn at an intersection, right? And we're kind of standing very awkwardly, like, behind it somehow, right? This is kind of, let's see, here's the intersection. Going this way. Right? It's making that turn. If we're standing behind it, first things first, right? If you're looking at an object, either even, looking at the front of the car or even behind the car, doesn't matter. If we're essentially looking at like this, I don't know what the best way to describe it is. Like, I guess it's normal 3D plane, right? So you have the surface of the road itself, right? You have the surface of the road itself. I'll try to like draw it kind of 3D. You have, this is the road, right? You have the surface of the road itself. You have the car on top. Let's say, forgive my like horrible drawing skills. But yeah, here's the surface of the road itself. The road is acting as a surface of contact, right? And here's the car riding along that road. What two forces should immediately kind of come to mind, just in general, right? Whether we have a car, we have a person, we have some other object, right? Let's say even the car wasn't turning. Let's say the car was just standing still, right? And we're standing behind it, right? What two forces should immediately come to mind in your free body diagram that we should draw out? FNFG, excellent, right? So we have some force of gravity, right, for the actual car itself, right? It has some weight, obviously. And also has a normal force, right, pointing upwards like this to keep that car level with the road and so that it doesn't sink through the road, right, or through the pavement. So we have these two forces, these vertical forces kind of canceling each other out. The weight of the car and the normal force, right, that keeps the car, level with the road. That's kind of, if we're looking at the object or the car here, stationary, right? When it's making a turn like this, right? When it's making a turn, let's think about this as now, here's the turn. If I were to, let me grab this and move. Move this over a bit here. Here's a turn, right? We can imagine this turn as having some kind of circular type path, right? So when you make a turn like that, you have kind of this, maybe a half circle, maybe a quarter of a circle, something like that, right? So in order to be able to make that turn, you must have like some kind of centripetal force, right? Something that's able to push that car essentially, right, to maintain that circular path, right? Otherwise, like, you're just gonna, like, if we try to make that turn, then instead of like keeping in this circular path, right, and making that turn, you would kind of go like this way and then you just kind of continue off that way. You wouldn't be able to make that turn without a specific centripetal force, right? So the idea here is that now we have this, if we're standing behind the car, we have normal force pointing upwards, force of gravity pointing downwards, and then if we were like literally just standing like right here observing the car, right, then something should be pointing this way, right? At least this is from a 3D perspective. And if we're looking once again strictly behind the car, instead of having it like angled like this, the force angled like that, it would immediately be to the right, right? So if we assume that this was, here's the intersection, right? Then in order to make that turn, I have to have a centripetal force kind of pointing to the right there, standing behind it, right? To be able to make that turn. And so the question is now, what type of force is going to be contributing this centripetal force here? What force allows a car to make a turn like that without slipping? That gives the car some kind of traction. Excellent, friction, right? Now the question is, what type of friction we have here? I saw kinetic friction. Now, kinetic, right? You'd think that kinetic makes sense here because kinetic motion, right? Cool, awesome. But Kinetic friction is specifically when you have an object sliding along a surface, right? Does a car, I mean, well, unless if you're in the snow, right, you don't have all-wheel drive, then you're gonna be a goner. Um, at least we wouldn't like a car to be sliding or slipping across the pavement like that, right? In perfect conditions, what does a car actually do? What do you notice about the tires on your car? They have some kind of like they have like little grooves. I don't even know what you're supposed to call them. Like little, I guess, little pieces of I don't know or something. Like there's little grooves in the tires, like thread, whatever. I don't know. That help to grip with the surface, right, of the road. And so this gripping with the surface of the road, right, helps the car refrain from like slipping, right? Because if the tires were just smooth, right, it wouldn't able to like grip with the surface of the road, and the tires would just spin and slide everywhere, right? Especially in the snow. And so there's just kind of this grippy surface to a tire that allows a tire to grip with the road and allows um, the car to make that turn without slipping and sliding. So the key here is that slipping and sliding kind of mentality here, or this idea. And so whenever we want to prevent slipping and sliding of something, we're usually concerned with static friction, right? Kinetic friction is going to be specifically like literally sliding, like an object sliding along another surface, right? But here the car isn't sliding; it's gripping with the road. It's trying to make that turn. It's trying to maintain contact with the surface without slipping and sliding. And so that means that the centripetal force here would be I almost said spring force, the static friction. So that is kind of how we would label our free body diagram, at least viewing the car from behind, right? You would have normal force pointing upwards, gravity pointing downwards, and then your static friction is pointing to the right, um, especially with that diagram where they're trying to look at, that car is already making the turn. So they had the car like here, and you're essentially behind it, standing looking this way. And so if you're standing directly behind the car at that moment when it's making the turn, normal force is pointing upwards as usual, right? Gravity is pointing downwards as usual. And then, like, you basically see the static friction pointing to the right, which would, from your position, it looks to the right. From an aerial position, it is basically towards the center of the circle, which would kind of be more angled this way. So it's almost like if you were to think about going to like a Google Maps like street view versus like an aerial view. If you're on aerial view, you can see that it points kind of at an angle towards the center of the circle. If you go to street view, then you're just standing behind the car like that, and it looks as if that it's pointing to the right. So here's like what I'm looking at here. So here's to the right if I'm standing right here, where I have normal force like that, and then gravity downwards, right? So if I'm sitting directly behind it like that, that's why I see the static friction there to the right. So that might be a good analogy to kind of think about it, like an aerial view versus like a street view, essentially. But that's kind of how to draw it. Like I might have spent too much time like explaining this free body diagram stuff, but like I saw way too many students miss this problem on the exam last semester. So, and it's because specifically they drew the static friction at an angle as opposed to just to the right, which is what they were intending when you view it from behind. So hopefully that like idea of like street view, quote unquote, and like aerial view kind of makes sense to figure that out. Um, but for part B, they want us to calculate the speed of the car in units of meters per second, right? So we want to figure out what V is, right? We want to figure out the speed of the car in units of meters per second. Now, for V, and we mentioned this earlier with the astronaut problem, right? We have it as being defined as the radius times your angular velocity, or we can expand that and say that it's equal to 2 pi r over t, right? So 2 pi r over our period here. Now, what was I going to say? So, okay, so we have the radius is 310 meters, so we have access to that piece of information. Another really important piece of information that we have here is the fact that the driver takes 4 minutes to circle the track 3 times, right? 3 revolutions, 3 times to circle the track, right? 3 whole revolutions in 4 minutes, right? So if we think about revolutions per minute, right? 3 revolutions 3 times around the track in 4 minutes. That unit of revolutions per minute, what is that referring to when we look at revolutions per minute? Frequency, excellent, right? So this is our frequency here. And so this revolutions per minute is our frequency. Our period is defined as the amount of time it takes for 1 revolution, while the frequency is how many revolutions can we do per second, right? So frequency is how many revs per second, how many times can we go around the track per second, while the period is how long does it even take us to do 1 full lap, right? And so if we figure this out, this gives us our frequency, right? This is essentially just, well, I don't want to do it in minutes. I have to convert things from minutes to seconds, right? Because that's the SI units for frequency, right? So 3 revs for 4 minutes, right? Where there are 1 minute, it's 60 seconds, right? So if I figure that out, that gives me my frequency, right? And my frequency, I know, if I look at my equation sheet as well, is equal to 1 over my period. Well, if I go back to this equation here, 2 pi r, 2 pi r, oh my bad, and then over t, well, divided by t is the same thing as saying 1 over t. So if I know that frequency is equal to 1 over period, if I just figure out my frequency, I can plug this in here and be able to get my velocity, because 2 pi r over t is the same thing as saying 2 pi r times your frequency. So if you do that, figure out your frequency, and you figure out your, if you plug in your radius and everything like that, so 2 pi times 310, and then times, so it'd be 0.75 times 1 over 60. This is 0.75 times 1 over 60. And then from that, you should be able to get your velocity. I believe, let me just calculate this out real quick. So 2 pi times 310, and then divided by the, or not, well, I could do period or multiply by frequency, same thing. And that should give me 24, yeah, something around 24 meters per second, roughly. 24.4, 24.3, something like that. For my velocity, right? And then the next part is kind of an extension of this, because they're asking now for the mass of the car, right? Well, how does mass relate to the velocity? Well, if we're dealing with things in terms of like centripetal force, centripetal acceleration, all of that, they told us that the centripetal force was 4,600 newtons, right? Well, we know that the centripetal force is equal to mv squared over r. Well, we have our v, we have our r from before, right? They gave us our radius was 310. We found our velocity from part B, right? And then from that, we can just divide those values over to figure out our mass. So this would be like 4,600 times the 310, and then divided by your v squared, and I think that was like 24 squared, 24 meters per second squared, roughly. And that should give you a mass of like 2,415 kilograms, I think. Does that make sense for part B as to how we can figure out the speed of the car? And make sure, obviously, that you're matching your SI units and stuff, because you could easily look at 3 reps per 4 minutes and say that's 0.75, that's my frequency, and then plug that into the equation without making sure that you convert to SI units. So converting to SI units is really, really important, because otherwise you'll get your answer off. But yeah, any questions about B? I'm going to take that as a no, I guess. Really, we're pretty much done, because part C is like asking us to verify information that we figured out from part A anyway, which is they're asking for what force is responsible for the centripetal acceleration. Well, the force that would be contributing to the centripetal force would be the one that would be responsible for centripetal acceleration. In this case, it's the static friction force. The 24 was the speed that I calculated, meters per second. Unless I plugged something in wrong. Let me double check. 0.75 divided by 16, that gives me my frequency. And I can just multiply by 2 and 10. Yeah, you got 24.3 something, yeah. Yeah, 24.3 or something like that. What is flipped? What are you referring to as being flipped? .310 should be at the bottom, 24 at the top. Let's see here. So we have your 2 pi r over t. Your r is your radius, that's 310. So 2 pi times 310, and then multiplied by your frequency. I don't think the 310 should be at the bottom, no. So let me rewrite it here. So if we have v is equal to 2 pi r over t, and that's the same as 2 pi r over frequency, or times frequency, and 2 pi times 310, and times our frequency. Our frequency was that 3 revolutions per minute, per 4 minutes, and then 1 minute is 60 seconds, and then that's how we can get the velocity there, or the speed. But yeah, might be a long shot, but like, because I almost like misunderstood this too. When I read 310 meters at a constant speed, like I don't know if like I went like partially dyslexic for like 3 seconds, but like I grouped that together and I was like, I saw meters at a constant speed and I was like, oh, 310 meters per second. But then that would have been a ridiculously fast car. Not really, actually. No, I take that back. That might be a fast toy car, but not a fast car. If it was 310 kilometers per second, then sure. Actually, no. Now if I think about that, I'm stupid. Yeah, no, that is a ridiculously fast car. That'd be like, if I calculate that off the top of my head, that's like 1,000 something kilometers per hour. Oh my god. Yeah, no, that would not be a toy car. That'd be like a giga car. Yeah, I can go back to my work for C was just looking at what force was responsible for centripetal acceleration. Do you mean B, like, or this part right here? Danielle, did that make sense? Like, I just want to make sure that we're on the same page, or are you still kind of unsure? Oh, gotcha. It's yeah, 40. My bad. I thought you were talking about another part. So 4,600 times r over v squared equals m. Yeah, so your r should be on top. But yeah, if this was 310 meters per second, that would have been one fast car. But yeah, any questions at all about this problem? Anything you guys want me to reiterate or repeat or anything like that, I'm more than happy to do so. Okay. For sake of time, I'm going to take that as a no at the moment, and then I will skip to the what was the next written problem that people want to go over? Problem 3. Okay, so that's a center of mass problem. So, written problem 3, center of mass. Alright, so it says a 6-meter long uniform wooden board with a mass of 5 kilograms is placed so that the left 2 meters of the board are on the surface and the right 4 meters hang off the surface. A 10-kilogram brick of negligible size is placed on the left end of the board. Take the origin of your coordinate system as the right edge of the surface, as shown. Okay. A lot of interesting information here. Number 1. When they say a uniform wooden board with a mass of 5 kilograms, what does uniform mean? What should we immediately think about when we're thinking about uniform? Something being uniform. Yeah, what is in the middle exactly? That's absolutely right, but what exactly is in the middle? Center of gravity, excellent, right? So center of gravity of the board, for a uniform wooden board like that would be in the middle. And so, let's see here. So we have this brick, we have the board, right? Now, if we were measuring from the left, from where the brick is located at, what would be the distance at which we would find the center of gravity? Let's see here. They 6 meter long uniform. Yep. Mm-hmm. Yep. So it's a 6 meter long wooden board. If measured from the left, where would the center of gravity be located at? 3, right? So we can say X board from the left is 3 meters. Well, the issue here is that this problem is wanting you to consider things not measured from the left, but measured from that central point right there at 0. Not really a central point, but that 0 point there at the edge of the surface. So if measured from the edge of the surface right there, where would that center of gravity be? If measured from the center of the, or from the edge of the surface there, where would the center of gravity of the board be then? Would it be 3 meters? Would it be 0? Because remember we said if measured from the left, it's 3 meters. So if we measure from that 0 point, then it would be close, not 1.5, right? Because it's a 6 meter long board, so the exact middle would be at 3. And so if you go from the brick to that edge of the surface, that's 2 meters. And then to get to 3 meters, right, you would go an extra 1 meter beyond the edge of the surface, right? So X board measured from edge of the surface, right, that's just 1 meter. They say 2. They said the left 2 meters of the board are on the surface, and the right 4 meters hang off the surface. Okay, so if you measure from the left where the brick is located at, right, the center of mass of the board, because it's uniform, would be 3 meters, right? But we're measuring from the edge of the surface. And so from the edge of the surface to that normal position of where the center of gravity is located, it would literally just be a 1 meter to the right from the edge. And that would be the same thing as saying 3 meters from the left. So 1 meter from the edge to the right is the same as 3 meters from the left, from the brick. Does that kind of make sense? So let me draw it here real quick. So we have this. Here's this board right here, right? Actually, let me adjust this drawing a little bit more. So here's our brick, right? From here to here, that's 2 meters, right? From here to the center of gravity of the board, that's 3 meters, measured from the left, right? But then they want you, because if we're measuring from the left, we're saying that this is 0 meters. I'm getting the 3 meters because this is a 6 meter long board. This whole thing is 6 meters. And because it's uniform, right? The word uniform is a key word essentially that means that the center of gravity would be exactly in the middle of the wooden board. So if it's exactly in the middle, then it should be like right here, right? And that distance, right, exactly in the middle of the board, right, 6 divided by 2 would be 3, right? So the middle of the board is 3 meters. 3 meters would be measured from the left here all the way to the middle point. That's 3 meters from the left. From the brick, from the left edge to the center, that would be 3 meters. But they want you, instead of measuring from the left, instead of calling this left point here at the brick 0 meters, they want you to say that this right here is 0 meters. Let me draw that in a different color. They're saying this is 0 meters, right? Right, so if from here to there, it's 2 meters, right? And from here to there, it's 3 meters. Then from here to here, it should be how many meters? One, right? So it'd be 1 meter. It'd be that extra, it'd be this little sliver distance here between 2 and 3. The brick measured from that edge right here would be -2, exactly, right? So it'd be -2. This part right here, this would be -2 meters because you're going to the left from that edge of the surface there. But measured here, going to the right until that center point, it would be 1 meter, positive 1 meter. Does that make sense? I want to make sure that that's all cleared up there. And this, like center of mass stuff, as opposed to torque, whether you move left or right from the pivot matters. Like going to the right would be positive x, going to the left would be -x. So you have to make sure to include those proper signs for the coordinates when you're calculating things out. Now, understanding of what's going on here helps so much to figure out the rest of that problem. And we actually kind of already figured things out here for part A, because they're asking what's the x coordinate of the center of mass of the board, right? So the center of mass of the board is at that 3 meter point measured from the left. If measured from the edge of the surface like we did in red, then it's 1 meter to the right. And so x board measured from the edge would be 1 meter. And so that would be your answer for part A. And someone, okay, so I think it was Malak, does that make sense? Like where I got the 3 meters and stuff, I just want to make sure to like check back in with you to make sure that you got that concept down. Okay, awesome. And does it make sense how we got like 1 meter to the right and negative 2 meters for the brick to the left? Okay, awesome. So that brings us to B, where they're asking for the x coordinate of the center of mass of the brick board system. Right, so now they're just asking for center of mass of the entire system here, which is the brick and the board. So the general equation for the center of mass would just be the center of mass of one object in the system times the mass of that object plus the center of mass of the other object in the system times the mass of that object, and then divided by the sum of the masses. Well, we only have two objects here, the brick and the board. So we have x board times m board plus x brick times m brick. And then we add together mass of the board and mass of the brick, right? We already said that the x board should have been 1 meter, right, measured from the edge of the surface there. And the mass of it was, let's see, that was 5 kilograms, right? And then we add that to the center of mass of the brick. Remember, if we're measuring from the edge of the surface there, we go negative 2 meters right there, so 2 meters to the left. So x brick is negative 2 meters. M brick, right, mass of the brick, was 10 kilograms. And then we simply divide by the sum of the brick and the board, right? So that would be 15 kilograms at the bottom here, 10 plus 5. And if we do that, we should end up getting the center of mass of the overall system should be negative 1 meters, measured from that edge of the surface. So really the center of mass of the whole system would kind of be like here somewhere, right? And if you think about it, that makes more sense because really your center of mass is going to be shifted towards the heavier object a little bit more. So this brick was 10 kilograms while the board was 5. So this kind of, shifts things over to its position more favorably. So that's why, like, here's our pivot basically at the red, like, edge of the surface here. That's our pivot. And so, here's our pivot here, right? And so since you have that heavier brick there on the left, it kind of pulls things towards it a little bit more. And that's why the center of mass is kind of shifted to the left there as opposed to the right. So it's kind of more like a sanity check there to make sure that your answer is kind of making sense with the information presented in the problem. But that brings us to C now, which is now a 6 kilogram cat begins. It's always a freaking cat. I don't know why. Like, they always want cats to die in these problems. It's never like some, I don't know, like object like a wrench or something, like a construction worker left. Like, it's always some cat that's about to like just jump off the board for some reason. I don't know. I have an issue with that for some, like, I don't know, like, it's always a cat. It's the lecture slides, it's a cat. Practice exams is a cat. The actual exam, it's a cat. It's very saddening. Yeah, cats have 9 lives, so maybe that's why they don't really care about the cats. But yeah, so we have a 6 kilogram cat that begins to walk on the board. What is the maximum distance d the cat can walk past the edge of the surface before the board begins to tip? This is like, expect this problem on the exam. I'm just gonna say that. Like, I wouldn't say like word for word, but like this style where it's asking how much can this object move past the edge of the surface before it begins to tip. Like, this whole begins to tip problem appears pretty much every semester. So like, hopefully I can, better explain this. I explained how to do it in one of my YouTube videos, but it's kind of a I guess, more of a difficult concept to understand and wrap your head around, but hopefully like I can be able to clear it up here. So the idea of when something begins to tip is when the center of mass of the system exhausts something called the base of support, right? So the base of support is going to be, as the name suggests, a base, a surface, a pivot, a fulcrum, something that is holding up the system, something that is maintaining the integrity of the system, something that's supporting the system, right? And so with these problems, oftentimes your base of support is simply the section of the board that is in contact with the building, the edge of the surface, whatever, right? So it's literally just the surface, the part of the surface that is in contact with the board. That would be your base of support. An object, right, or the system would begin to tip when the center of mass of the system goes beyond the base of support. It goes beyond that part of the surface that is in contact with the board, right? So if we're drawing this out again, right? So we have, here's our board, here's the, let's say we'll call this like a building, or they call it just the surface basically, right? That's our base of support here, right? It's the base that is supporting up this board, right? It's what's giving it integrity, maintaining its integrity, right, of the system, and holding it up like that, right? We define that this section here that's in contact with the building or with the surface, right, the surface edge, is 2 meters measured from the left here, right? 2 meters. Now, measured here, we call this 0.0 meters, right? So instead of saying that this left point was 0 meters, we set this edge, the very edge of the surface, the very edge of the base of support was defined as 0 meters, right? Now, when we say that the center of mass of the system exhausts the base of support, it means that it goes outside of that range that is holding up the system. So this is the range that is holding up the system, this little surface, this base of support here. When the center of mass, let's say here's the center of mass is going to be in yellow. If the center of mass lies anywhere within this base of support, right, even if it's at literally the very edge here, we're solid, right? That's the maximum we can go. Anywhere, any distance within this base of support, within where the board is in contact with the building, where the board is in contact with the surface. Anywhere within this range, we're good. The board is not going to tip. As soon as you exit this range, literally if you go 0.0000001 meters beyond this base of support, it's over with. You're a goner. So that means, or actually I should be asking this question, what is the point, where exactly would be, where would the point, like, okay, so where's the point that essentially would be the maximum the center of mass could be, to where, like, if we literally go anywhere else, if we literally shift a centimeter past that point, we would see the board tip. Where would the center of mass of the system be at a maximum, where if we shift literally a centimeter, a millimeter past it, we would see the board tipping? Where would the center of mass be to where it would, if we shift a millimeter and shift a centimeter, it would exhaust the base of support? It would go beyond the base of support. Where would that point be located at? Excellent. 0, right? Because like I said, the idea here is that you want your center of mass of the system to literally be located anywhere within this base of support, anywhere within this range here. This point where it's at the very edge of the base of support is your limit, right? If you literally tip over a single millimeter past that surface, past the building, right? Past the edge of the building, past the edge of the surface there, your center of mass goes beyond that point, then you start to tip over, right? So our center of mass, therefore, should be directly at that edge to where we have now exhausted the base of support, right? Or we're about to exhaust the base of support, right? It's that maximum point. If we shift literally a millimeter, a centimeter over, the board will begin to tip. So when you have this style of problem, when they're asking you when a board begins to tip, it's when the center of mass is at the edge of the base of support. It's not necessarily where the pivot's at, because remember, we could very well have considered this to be the pivot from the left, and we could measure everything from the left if we wanted to, right? The idea is more so, where is the board in contact with a surface? What is that range that it's in contact with a surface? Where does that range end? Wherever the range ends, right? Wherever you stop coming into contact with building and you start coming into contact with air, that's when that's where the center of mass should be, right? So here's your base of support, right? Here's your base of support right here. That's where the board is in contact with the building. This is the last point. This is the last point where if you literally go beyond it, you're in free fall. You're a goner, right? You're in contact with air if the center of mass goes beyond that point. So the center of mass, as long as it lies within that base of support, wherever the rod, wherever the board is in contact with the building, with the surface edge, whatever, right? However they choose to refer to it, as long as it's in contact with this supporting base, this base of support, right? As long as the center of mass is within this little range here, we're good. The maximum point would be where we would begin to encounter air, where we would essentially exhaust the base of support, where we would no longer have any contact with the building or the base of support, right? So this building is holding up the board, right? Making sure that the board is in contact with the building, is offering it a base of support. If we go past this edge of the surface right here, if we go past the edge of the surface, then we would exhaust the base of support and the board would begin to tip over. When I say or refer to going past this, I'm referring to the center of mass going past it. I'm not referring like directly to the cat going past that point. Because the cat could go somewhere here or somewhere there or somewhere there, right? As long as once we actually calculate the center of mass of the brick cat system, when we calculate the center of mass, as long as the center of mass, once again, lies within this base of support, we're solid. The maximum center of mass we could have is at the very edge of the base of support, at the very edge of the building, right? Where we would begin to encounter air, right? And so when the center of mass is at that point, that's when things would begin to tip. That would be your maximum, right? Anything beyond, any center of mass beyond this point, we'd be experiencing like tipping of the board and an imbalance in the system. Otherwise, as long as you lie within this base of support, you're going to see no tipping whatsoever. And so, yeah, it's not just a matter of like center of mass being located at the pivot, because they could say the pivot is the brick if we wanted to, or that left edge of the board. But it's more so dependent, like I said, on the range of the base of support. What part or how much of the board is in contact with a surface or a building or something like that. Whatever range that is equal to, like let's say if the board was shifted over to the left a little bit, to where instead of 2 meters is in contact with the building, instead of 2 meters being your base of support, maybe it was 4 meters, right? So you have 4 meters of range there that you can essentially kind of deal with and play around with, to where the cat can walk different distances along the board and have the center of mass of the system stay within that 4 meters or stay within that 2 meters. As long as you stay within that safety range, the base of support range, the board will not tip. As soon as you get to that edge, that's where you've hit the maximum. If the center of mass shifts literally a millimeter past this edge, right, and you encounter air, then the board will begin to tip over. I know I repeated myself like a million times there, But does that like clear things up and make sense, I guess, with regards to understanding this concept of base of support? Because you can see here this problem was like 5 points. I saw one too many students like butcher this problem last semester, because they're just, I guess they just didn't quite understand this concept of the base of support. But yeah, I mean, any feedback? Does it make sense? Should I repeat something? Anything that's unclear? Yeah. Yep. I'm recording it, and it's should be uploaded within like an hour, hour and a half after this session. But yeah, like I said, this was more of like a drop-in kind of thing, where like students just kind of like asked whatever questions they wanted on the practice exams and kind of went through those. Um, but yeah, and this is also for everyone else too. Like, if you guys have any questions, just let me know. DM me, send me an email, and I'll be happy to answer. I know like maybe some students have like low key kind of ignored like the past like couple of days, and I not my intention whatsoever. Like those who know me and have like contacted me like know I'm usually like on top of my game, but um, yeah, I just had like a rough past couple of days, so I'm getting back to like some older messages from students. So I never just like leave a student just hanging. So I'll go back and answer questions and stuff like that. But yeah, if in case you have any questions afterwards, yeah, just let me know. I'll be happy to answer. Mm-hmm. Is that making sense so far with this whole base of support thing? Okay, awesome, sweet. So that means then here's my question. I think we might have answered this earlier anyway. If we're trying to figure out the maximum distance the cat can walk past the edge, right? What value are we looking for? What is that called? Like the location of the cat, what would that be? So yeah, it would be a center of mass, right? So it would be the center of mass of the cat, exactly. Um, and so that's essentially what we're looking for. It's center of mass of the cat, the location of the cat along that system, right? So, um, what was I going to say? So, um, yeah. Okay, so we have center of mass then is going to be equal to the um, center mass of the board times the mass of the board plus center mass of the cat plus mass of the cat over mass of the board plus mass of the cat. Um, let's see here. Did I miss something? I think that's it. But now, okay, so would I also integrate the center of mass of the brick? I think I should. Yeah, I should. Um, yeah. So this is. I don't know why I got thrown off on that for a second, but I think for some reason I was just thinking of the brick as the pivot when I completely overlooked and forgot that we're literally talking about the pivot being right there at the edge of the surface. So mass of the brick as well, and then plus x brick times m brick. Yeah, there we go. So essentially we just kind of go back and substitute all those values again, right? So the center of mass of the board was what? Someone type it in the chat here, user mic or whatever. What was the center of mass of the board? So center of mass of the board was 1, right? So it was 1 meter to the right of that edge of the surface, right? And then the mass of it was 5 kilograms, right? And then the center of mass of the cat is what we're trying to figure out. Mass of the cat was 6 kilograms, right? How about the center of mass of the brick? So that's -2 meters there, right? And then mass of the brick was 10 kilograms. Yeah, when they say brick is of negligible size, the reason why they say that is because, like, when you're looking at things like center of mass and stuff like that, if you have like a really, obviously you have something like a board here, right? The board has a non-negligible size. It's 6 meters long. So the center of mass wouldn't simply just be located like, well, I guess since it is a uniform board, right, it would be located in the middle of that board right here. But for the brick, let's say if the brick was like huge or something, right? Let's say it took up more space than just this point right here. Let's say it was literally like this big, right? Then we would have to figure out, okay, well, maybe how long is this brick? How long is this brick? And then is it a uniform brick or not? And then figure out the center of mass of that brick and then measure it from the left and be like, okay, here's the center of mass of the brick. And that's what we're using for it. When they say it's of negligible size, it means that wherever the brick is located, that's the center of mass, right? So since it's located at the left end, we're just going to call it 0, right? That's center mass of it is at 0, or at least measured from the left. Measured from the edge of the surface would be -2. Otherwise, like, if the brick was like huge, let's say it was, I don't know, 1 meter in length, right? Then measured from this edge of the surface here would go back 1 meter. And let's say it's a uniform brick, then it would be straight in the middle here. So then the center of mass would have been like negative 1.5 meters, for example, right? But since they're saying that the brick, we can kind of ignore the size of the brick, it's small, it's negligible, it's trivial, then we don't really care about the size. And so the position of the brick is the center of mass of it, right? Otherwise, for something like you see here, like with a board, right, we have to like look at the length of the board, figure out where their center of mass is located, whether it's uniform or not. But since the brick, negligible size, wherever it's located is its center of mass. So that's what they mean by negligible size. So otherwise, like I said, if it has a specific size, right, then we have to factor that in when calculating to make sure that we get the proper center of mass. And then that gives us everything here, and then we're adding up the masses of all of them. So 6 plus 5 plus 10, right? I think, yeah, that works out. So, and we said that the center of mass is going to be 0, right? Which is going to be at that very edge of the surface right there. So if we multiply this over, this doesn't matter, right? Whatever this ends up being, we don't even have to calculate. When you multiply by 0, everything becomes 0. So this is 0 is equal to 5 kilograms. I'll just say, you know what, because I don't want to write like 5 kilogram meters for every single one. I'll just write 5, and then this is 6x, and this is like -20, right? So then we're left with -15 plus 6x. If we add the 15 over, then your x cat, right, this is x cat, the center of mass of the cat would be around 2.5 meters. And that would be 2.5 meters past the edge of the surface. So that means that the cat can literally walk 2.5 meters past this edge of the surface, right? And still just barely have the board in contact with the building or with the surface, right? If it goes 2.50000001 meters, the board is tipping. It's over with, right? So that's the meaning there of your answer there at the end, that the cat can go 2.5 meters past that edge of the surface and have the center of mass of the entire system be located at that very edge. That's your maximum. If the cat walks any distance past that 2.5 meters to the right, if it goes 2.50000001, the board will begin to tip because the center of mass of the system will now be beyond this yellow range that we defined. It will be beyond this base of support. But yeah, that's probably the easiest way to solve this problem. I think you would be also able to solve this using torque, but that's unnecessary. I think it's much easier and much more straightforward, especially with these like quote unquote begin to tip problems, to use center of mass. Like, it's a very common problem that they pull on the exams, and I think if you are able to understand how to like process the information from this, and hopefully I did a good job of like explaining how to think this through, then you should be in good shape for like the center of mass type problems for the exam. But yeah, so does that make sense for problem 3? Any questions at all about problem 3?
Yeah, that makes sense.
Okay, awesome. One second here. I gotta switch earbuds. One died, and I gotta switch to the other one. But yeah, what? Oh my god, I did not check the time. Yeah, so I guess we went a little bit over time, but I don't know. Like, I guess I can kind of end the recording here because I have to get to some work actually after this. But I wanted to kind of ask you guys as well, like, what's your feeling so far with these concepts, and kind of also just sort of get like a makeshift survey essentially. Like, how's everything kind of going with the concepts? How's everything going with the semester? Have you been, like, I guess, watching my videos? Do you find them beneficial? Like, anything I should edit or add, like, change about how I support the course? Anything I should, know or anything like that? Any questions you guys have? Any comments? Any concerns? Mm-hmm. Yeah, yeah. It's Saturdays and Sundays, 6 to 8 p.m. I'll have like open drop-in sessions, and I've had students come and ask about online homework. I've had students ask about quizzes, written homeworks. I keep those as open drop-in sessions. I don't do like dedicated like written homework reviews anymore because from what I've seen so far, like the written homework is pretty much the exact same as last semester. So it's like, I mean, I don't mean to like be lazy, but like the work is like already there. So, um, like I leave it more for like, like there's very specific questions like about concepts that you guys have, that you guys are unsure about. I want to make sure that like I'm not like repeating myself because like I'll basically just like go over the same problems, explain it the same way. But like if you have more specific, more niche things that you want to ask about, then those like that's why I kind of kept them open this semester as opposed to like having dedicated um, like sessions for like the homework or something like that. But yeah, I'm open to asking, getting questions about quizzes, online homework, written homework, anything that you guys have issues about, regarding like the course, even advice, for how to study or anything like that. I'm more than happy to share my experience. But I'm glad to hear that the videos are helping. I like it's always funny and to interact with students at like outside of or yeah, I guess I had some students like in a class that I was taking that I guess they recognize my voice. So it's always funny like to have those like interactions. But um, Yeah, no, I'm always happy to see that students are benefiting, and I'm always open to criticism. Like, tell me my videos are shit. Tell me like I explain things in a horrible way. Like, I will try and explain them again. I'll try my best because, like, I'm not one to be stubborn and say like, okay, this is how it is, and this is what we're gonna do, and that's the end of it. But yeah, yeah, absolutely. I'm gonna go ahead and end the recording as well here, so I can make sure I can upload that as soon as possible after the session. But yeah.